by the power of Grayskull.
Well, that was a flashback. Welcome back, guys. My name is Miss Danielson, and today we're having a look at laws of indices. I hope you joined us for our previous lessons on square numbers and cube numbers. If not, I'm linking them down in the description box below, so you can check those out before you get started. Otherwise, let's get into it. Exponents, powers, and indices. Oh my, they're three different words that mean the same thing. Nothing to be afraid of. It's just that little number up there at the top. And it must be little and it must be up top. The bottom number is the base, and that top number is called either the exponent, the power, or the index. Now we've seen indices before when we were looking at square numbers. Square numbers are the result of raising some base value to the power of 2. X squared, for example, means x raised to the power of 2. And the power tells us how many times we need to multiply by that base. So x to the power of 2 means x times x. There are two x's being multiplied together. Another example might be 5 to the power of 2, also known as 5 squared, or 5 with an index or exponent of 2. And that just means multiply 5 times 5, two 5's being multiplied together. We call the 5's the square roots of the number 25, because the square tree with the number 25 on it has got roots of 5. Cube numbers specifically have a power of 3. That means that we're going to multiply the base value by itself 3 times. So for example, x cubed, or x to the power of 3, or x with an exponent or index of 3, means x times x times x. 3 x's being multiplied together. We could use a number to show this as well. So 2 to the power of 3 means 2 times 2 times 2. And in the example that we did on our cube numbers lesson was to say that cube numbers grow on cube trees and they come from their cube roots. 2 would be the cube root of 8, because 2 times 2 times 2, or simply 2 cubed, is equal to 8. The purpose of an index is to simplify an expression, just as we do with coefficients when we group like terms that are being added together. So, for example, a plus a plus a, we could say that that's 3 a's minus an a, well, that would make 2 a's. 2 is the coefficient that I'm using to show how many a's in total would be. Another example would be 2b plus 3b minus 1b. We could use a coefficient to show how many b's that would be. 2b's plus b would be 3b's, plus another 3b's, that would be 6b's, minus a b, that would be 5b's. So I use the coefficient 5 to show how many b's there are. There are 5 b's altogether. Now this does not use indices because here we're just adding or subtracting like terms. But when we are multiplying a value by itself repeatedly, like 3 times 3 times 3 times 3 times 3, it would be much easier if I were just to tell you how many 3's am I multiplying together. That's 1, 2, 3, 4, 5. I am multiplying 5 3's together. I am not adding 5 3's though. So this is 3 to the power of 5, or 3 with an index or exponent of 5. W times W times W is another example using algebra this time, showing that I'm multiplying 3 W's together. So I'm going to write that as W to the power of 3, or W with an index or exponent of 3. Or in the case of powers of 3, as we've learned before, we could also say W cubed. Just as we can use exponents or indices to simplify expressions, we can also expand the expressions out when indices have been used. For example, I could say 7 to the power of 5. What does that mean? It does not mean 7 times 5, which is a common mistake that people make. It means 7 times 7 times 7 times 7 times another 7. That is 5 7's being multiplied together. Another example might be x to the power of 8. x to the power of 8 is not the same thing as 8x. This is 8x's being multiplied together, not 8x's being added together. This is x times 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 x. Now I know what you're thinking. Why would I ever want to expand all of that out when it's so much simpler to read and to write as simply x to the power of 8? And the reason for that is so that we can more clearly understand what this term means. So we are going to use this expansion in order to help us explain the index laws. Once they've been explained, you do not need to expand out these terms every time. You can just use the index laws directly. The first index law we're going to look at is the multiplication law. And we need to have clear that these index laws can only be used for index terms with the same base value. Remember, the base value is that big number down at the bottom. So for example, 2 to the power of 3 times 2 to the power of 2. These two index terms have the same base. Both of their bases are 2. Let me show you how we could expand this out and from that deduce the multiplication law. 2 to the power of 3 means 2 times 2 times 2. Timesing that by 2 squared means timesing by another 2 and timesing by another 2. All together, have a look at that. How many 2's are being multiplied together there? 5, right? So we'll simplify that and say that that is 2 to the power of 5. Let's try that with x to the power of 5 times x to the power of 2. They both have the same base. They both have a base of x. So when we expand that out, you will see that I'll have a bunch of x's multiplied together. Altogether, how many x's are being multiplied together? 7, right? So that would be simplified to x to the power of 7. I hope you've noticed that this is not the same thing as 5x plus 2x. Obviously, it's not the same, but it's a very common mistake that people make. 5x plus 2x would be 5x's added together, plus another 2x's added on. That would be 7x's added together. So although they're not the same thing, you can see the similarities of maybe why people get these confused. The multiplication index law helps us to simplify these expressions without having to expand them out. When the bases are the same, we can simply add the indices. So 5 to the power of 7 times 5 to the power of 18, that would take a very long time and be very difficult to accurately expand that out and then simplify it down. But using the multiplication law, I know just to add my indices. 7 plus 18, that's 25. So I would have had to write 5 times itself 25 times in order to expand that out. So now that I know the law, it's not necessary. Go ahead and write this down because it's going to save you a lot of time in future. Next, let's take a look at the division law. Again, these index laws can only be used if the bases are the same. So for example, 4 to the power of 5 divided by 4 to the power of 3. The bases are the same, they are both 4's. Let's expand this out again so that you can see where the law comes from. This means 5 4's are being multiplied together, and that result is being divided by 3 4's multiplied together. We can simplify this fraction by dividing both top and bottom by the common factors. They both have 3 4's in common. If I divide the top by 4 3 times, I would just be left with 2 4's. So 4 to the power of 2. If I divide the bottom by 3 4's, I'll be left with 1. When you divide a value by itself, it gives you 1, not 0. So that would end up being 4 squared. See, I've taken off 3 4's from the top, I've taken off 3 4's from the bottom, and I'm left with 2 4's on the top, 4 to the power of 2. Let's see another example to make sure that's clear. X to the power of 3 over x to the power of 2. Expanding that out, once again, I can divide both the top and the bottom by some common factor. I could divide the bottom by x times x. That's dividing the bottom by all of itself. And I could divide the top by x times x. If I got rid of two of the x's on the top by that division, I would be left with a single x on the top. If I got rid of those two x's on the bottom by dividing, I would be left with 1 on the bottom. When you divide a value by itself, it leaves you with a value of 1. So this would leave me with x over 1, which is simply x. Any value divided by 1 is simply that value itself. Note one thing, that x is the same thing as x to the power of 1. To explain that, let's have a look at the division law. We can use the division law to do this really simply by simply subtracting the indices. As you saw, both times I did this, I looked at the number of the bases there were in the denominator of the fraction, and I saw that I could cancel out the same number of that base from the top or numerator of that fraction. So I've subtracted 3 4s from the 5 4s I had on top. I've subtracted 2 x's from the 3 x's I had on top, leaving me with 1 x. X to the power of 1 is the same thing as simply x. Because remember that power says how many of these x's should I multiply together? 1? Well, that would just be x itself. Let's have a look at another example using the division law. 9 to the power of 12 divided by 9 to the power of 7. I could write that as a fraction, so I'd write 9 times itself 12 times on the top and 9 times itself 7 times on the bottom, but I'm just going to use the rule. 12 minus 7 is going to give me 9 to the power of 5, because of these 12 9s, I would have cancelled out 7 of them. 12 minus 7. Write this rule down. It'll be really helpful and it'll save you a lot of time when these exercises come up. Next, let's check out the power of a power law. I'm starting right in with an example so you can see what I mean. 6 to the power of 3 is in brackets and I'm raising that to the power of 2. So this index term has 2 powers acting on it. First, what we need to know is that 6 to the power of 3 means 6 times 6 times 6. And if we're squaring that, we are multiplying everything that's inside that bracket by itself. So I have got that bracket multiplied out twice. 2, 4, then 6, I can simplify 8. Using simple multiplication law. 8. How many 6s now, rather than expanding all of that out, that simplifies to just use the power of a power law. Let's try another one. Looking at variable exponents that we were given squared in the question, raised to the power of 4. And the exponents of our answers, would be x squared multiplied by itself 4 times. All we need to do is, or if I wanted to expand out the x squared, 3 times 2 is 6, x times x, and 2 times 4 is 8, 4 times. For example, if I had 2 to the power counting of 12, out how many x's are being multiplied to the power together, of 5, I wouldn't want to write that out. 2 to the power of 12 multiplied 5 times, and I can simply use the power of a power law and say 12 times 5 is 60. Go ahead and write this rule down because this is the third of the index laws that you must know. And hopefully you now understand it, so it won't be difficult for you to remember. Let's try some practice now. For question 1, you need to use indices to simplify this, so write the base to some power. Remember the bases must be the same for you to be able to group them. Question 2, expand out in full. So I want you to write these questions in the same format as you see above in question 1. Question 3, use index laws to simplify. So remember your multiplication, division, and power of a power law. And remember you can only use that on index terms with the same base. And finally, question 4, simplify and evaluate. That means use index laws to simplify this before you actually work out your answer. Go ahead and hit pause now, copy your questions, work out your answers, and hit play when you're ready to take this up. I hope you've had a chance to hit pause, because here come your answers. For question 1, for question 2, for question 3, notice with D, 7 plus 6 minus 12 gives us 1, but when there's an index of 1, we don't need to write it. 6 to the power of 1 is the same thing as 6. And if we're simplifying, we want to write it the simplest way. Part E, F, and G. For question G, notice I didn't fully group it because I didn't have the same base. A base of 7 cannot group with an index term with a base of 2. Question 4. Now, how did that go? Hopefully it all makes sense, and I hope you found this lesson helpful. If I've left anything at all unclear, please let me know in the comment section down below, because this is just the beginning, so we need to make sure we catch out any doubts before we get any harder. Until next time, keep practicing, and I'll see you soon.